Hello, my students. What this brief video will do is give us a refresher on solution concentrations, namely focusing upon the differences, the tips for using these, and introducing the concept of normality, which we have not seen thus far. It is extraordinarily important to a chemist to be able to communicate the exact amount of solute present per the amount of solvent, hence concentration expressions. We're familiar with percent by mass. Just be careful that you are indeed taking the mass of solute over the mass of the entire solution, which is the grams of solute plus the grams of the solvent. For molarity, that is the go-to expression for chemists, namely because we have moles of solute, and being in moles gets us right to our stoichiometric relationships for analysis. Also, the majority of solutions we work with are liquid in their final state, and we measure the amount of liquid per volume in liters or milliliters. So this is just a nice, friendly kind of concentration expression that lends itself to stoichiometry as well as ease of measuring. We'll come back to normality in a moment. Mole fraction is a ratio of moles, and just be careful as to what you're expressing the mole fraction in terms of. The solute, then it's mole of solute per entire moles, or mole fraction of solvent, then it's mole of solvent over the entire moles. Molality is mole of solute per kilogram of solvent alone. This is particularly useful when our solution is undergoing a change in temperature. We will see this mostly when we investigate colligative properties. The presence of a solute affects the physical properties of the solvent. Recall learning about freezing point depression, boiling point elevation, vapor pressure lowering. We're changing, namely the temperature. If we're undergoing a change in temperature, then we need variables that do not change when temperature changes. Mass does not, where volume does. So that is where molarity fails us and molality delivers. So we will use this primarily at the end of our chapter. We're also going to talk about osmotic pressure. We haven't seen that yet. And so that's where we'll need molality, a lowercase m, versus molarity, a capital M. So normality. Normality, a capital N, is equivalence of solute per liter of solution. We will utilize normality to express concentration when we're dealing with acids and bases and also oxidizers and reducers. So what is an equivalent? An equivalent with acids and bases is the quantity of acid that yields 1 mole of hydrogen ion in solution, or the quantity of base that can react with 1 mole of hydrogen ion in solution. This will be the primary application for normality. However, an equivalent is also the quantity of oxidizing or reducing agent that can accept or furnish 1 mole of electrons. So let's specifically look at what this means and how can we interpret this for specific acids and bases. If we have 1 mole of HCl, that 1 mole of HCl can ionize to create 1 mole of hydrogen ion. So 1 mole of HCl gives us 1 equivalent. 1 mole of NaOH can react and neutralize 1 mole of hydrogen ion. So thereby 1 mole of sodium hydroxide would be 1 equivalent. 1 mole of sulfuric acid potentially, fully, can give us 2 moles of hydrogen ion, thereby 2 equivalents per 1 mole of sulfuric. 1 mole of calcium hydroxide can neutralize 2 moles of hydrogen ion. So 1 mole of calcium hydroxide is 2 equivalents. Phosphoric would be 3 equivalents per mole. Aluminum hydroxide would be 3 equivalents per mole. So we'll utilize the relationship that 1 mole of phosphoric, for example, is worth 3 equivalents whenever we're doing problems with this. So if we would have a 0.5 normal HCl solution, well, that means we have 0.5 equivalents per liter of solution available. And we'll see this again more specifically when we look at example problems. In the second page of your packet, I have just reminded you of a key to problem solving. We want to be able to see our concentrations as conversion factors. So reading through this and showing us an example, if we would have a 0.14 molar sodium chloride solution, well, that means there's 0.14 moles of NaCl per 1 liter of solution, where this accounts for the volume of the solute and the solvent. Where if it would be a 0.14 molal sodium chloride solution, this would be 0.14 moles of NaCl per 1 kilogram of solvent. And unless otherwise told, we assume that our solvent is water. So it's understanding what the concentration expressions are, how they can be expanded to be conversion factors in our problem solving. So what I would like to do now is to go through some of the examples that are on the next page, highlighting some tips. The first example deals with mass percent. You are finding mass percent, and we simply need to be able to extract out what we need for our equation. For mass percent, it's grams of solute divided by grams of solution. Now, as long as your units are the same, you can all be in grams, all be in kilograms, even though commonly we'll be in grams. So just be sure that you're taking the 20 grams. Now we need to convert the mass of our solvent to grams, and then add our solvent to our solute, being careful of sig figs, and you're going to get 7.41%. You need to identify what your solute is when we're labeling. If you simply communicate your answer as 7.41%, percent of what? In this case, our solute is sodium chloride. And again, otherwise told, our solvent is water, and here we are confirmed that our solvent is water. In our next example, the question is, how would we prepare 455 grams of an aqueous solution that is 6.5% by mass sodium sulfate? We're looking for a recipe. If I ask how would you prepare, how would you make, you need to give me full instructions. How would you prepare? I would always attack these problems through dimensional analysis if possible. So we're asked for 455 grams of solution, and our solution, every 100 grams of solution gives us 6.50 grams of sodium sulfate. This then will give me my answer of how much sodium sulfate, and if I take this, subtract it from 100, then I get, from 455, then I get the mass of the water. So if I look here, I actually solved here per the equation, but you'll get the same answers. So here we would get the 29.6, then taking the 455 minus the 29.6. With sig figs, we're bound to the whole number, so thereby 425 grams, and water's our solvent. So that would be the full answer. For number 3, we could solve it per the equation or solve it with dimensional analysis. So showing us through dimensional analysis. As it said on the prior page, we can use our concentration expression as a conversion factor. Okay, so you're starting with 258 milligrams of potassium iodide. Well, we want to get ourselves out of milligrams into grams. And we have 2.50 grams of potassium iodide in every 100 grams of solution. And so setting it up simply in this way will get us how many grams of solution given this percentage and given this amount of potassium iodide will contain that. And our answer is 10.3. In number 4, it's asking for molarity. Now, I gave you grams, so you could solve for moles separately and then input it into the equation. We're given milliliters, and you have to obey the equation. Molarity is mole per liter of solution, so we need to get into liters. So you could do it in a stepwise fashion. We could also solve it with dimensional analysis. So if we have 0.44 grams of NaOH, we know we need moles of NaOH per liter of solution at the end of the day. There's 40.01 grams of NaOH for every 1 mole of NaOH. So there's the numerator we need. And I need per liter, well, I have 250 milliliters of solution. And putting on the numerator will not work. I need volume to be in the denominator. So that lets me know right away I didn't approach it correctly at first. So I went mole per unit of volume, so I can put this under 1, and then 1,000 milliliters will give us a liter of solution. And so we can see I'm left with moles per liter of solution. So I could do it as dimensional analysis or do it in the 2 separate steps that you see here. Number 5, I showed with dimensional analysis. Let me get rid of number 4 so you can just see that directly. So if you want to take a look through my work, number 6, now the only thing with number 6, for molality, it needs to be per kilogram of solvent. And we're given volume of water, liters of water. Now, you always hesitate to assume. However, it's okay sometimes. Whenever we need to make the assumption and trust the density of water being 1 gram per mil or 1 kilogram per liter. And so if you're given liters, those directly communicate to kilograms, or milliliters directly to grams. Number 7, I did with dimensional analysis. So you can take a look at my work for that. Now it asks for how much water. Unless I specify, amount is really whatever you decide. Now water, we would measure in terms of volume practically, but you could have left it in liters, milliliters, or actually communicated it as grams because amount is so general. For 8, that is dealing with mole fraction. You just have to be careful that you're communicating the right perspective. So I went from grams to moles for each of my components. Make sure that you add for your denominator for total moles. And if you're finding the mole ratio for each of your components, they should add up to be a total of 1. I'm going to stop this video here and then come back to do the last 3, these dealing with normality, and this just being a little trickier with the math.